Thanks for joining me today. Today we are going to start talking about probably one of the most important topics in all of chemistry. One of the things that we're going to use a lot. It's a concept that is not really super complicated. However, some people do find it difficult because of the numbers that are involved. What I'm talking about is counting numbers. So counting numbers are defined as numbers that are always the same, no matter what type of thing you're talking about. You're familiar with counting numbers already. We use them a lot. So you are familiar with things like a dozen. A dozen roses is 12 roses. A dozen cookies is 12 cookies. A dozen jelly beans is 12 jelly beans. It doesn't matter what thing we're talking about, a dozen is 12. Another counting number that is common in daily life sometimes is a gross, which is a dozen. 12 times 12 is a gross, 144 things. So if you have a gross of bananas, you have 144 bananas. So counting numbers are not all that complicated. You're familiar with them. You've used them before. So a mole is just a counting number. It's a very, very big counting number. One mole is 602 and a whole bunch of zeros of things. That's 602 hexillion things. So 602 and then 21 zeros. That is a huge number. All right, you can also sometimes see it written down in scientific notation as 602 times 10 to the 23rd things. That's what a mole is. And it's just a counting number. So if you have a mole of anything, you have 602 hexillion things. That's what a mole is. So before we get in more into it, let's talk about how big that actually is. How big is a mole? Well, the average thickness of a piece of paper is 0.1 millimeters. That's a tenth of a millimeter is how thick the average piece of paper is. And if I were to take a mole of paper and stack it up into a stack that's 1 mole of sheets of paper, that stack would reach the moon and back 80 billion times. Billion with a B. 80 billion times, there and back. 80 billion times. That should give you an idea of how huge that number of 602 hexillion is. So let's do another one. The average length of a housefly buzzing around. A housefly is about 0.6 centimeters in length. If I were to take those houseflies and lay them head to tail over and over, and I had a mole of houseflies head to tail, it would go around the circumference of the Earth at the equator, the widest, thickest part of the Earth, all the way around 90 trillion times. It's a huge number. A mole is a huge number. Let's do another. The average volume of a jelly bean is 1.18 cubic centimeters. 1.18 cubic centimeters. If I had a mole of jelly beans, that would be roughly the same volume as 3 times the size of our moon. So it'd be like having 3 moons worth of jelly beans. That is huge. So why do we have a number that is so big? Why do we need to use a number of 602 hexillion things? Well, it's because atoms and molecules are so incredibly small. And we have so many of them when we're dealing with chemistry. Atoms and molecules are so incredibly tiny that we need a huge number to count them. So, for example, a mole of water, 602 hexillion molecules of water, would take up a volume of a little less than a tablespoon, or a little more than a tablespoon. That's not a whole lot of volume, but there's 602 hexillion molecules in that tablespoon of water. So where did the idea of a mole come from? Well, originally, the mole was defined as the number of atoms in 12 grams of carbon-12, the isotope of carbon that has 12 protons, or 6 protons and 6 neutrons, has an atomic mass of 12. That is the originally defined 12 grams of carbon-12. Well, in 2018, the scientific world was in the process of redefining a lot of the SI units that we use, and they redefined the mole. The mole is now officially defined as
6.022140076 times 10 to the 23rd particles. Things, anything you have. 6.022140076 times 10 to the 23rd things is the official definition of a mole. Now, this was chosen so that the mass of 1 mole of an element would be numerically equal to the weighted average atomic mass measured in atomic mass units, also called Daltons, of the elements on the periodic table. Now, if you're in my class after this video, there's going to be a link to a video by a guy named Mould that does a pretty good explanation of why we use a mole and why the mole is. I'm not going to take the time to get into that. I'll just leave a link to his video. If you're watching this on YouTube, I'll leave a link in the description box below to Stephen's video on that. A way of defining and explaining the mole. That's pretty good. So given that definition of 6.022140076 times 10 to the 23rd particles was chosen so that the mass on the periodic table is numerically equal to the atomic mass measured in atomic mass units. That means the mass on the periodic table as measured in grams. So when you look at the mass on the periodic table of oxygen is 15.999. That's 15.999 atomic mass units is the official unit, but it's also numerically equal to the mass in grams of 1 mole. So you can also say that the mass on the periodic table is 15.999 grams per mole. So there's 15.999 grams of oxygen per mole of oxygen. So if I have 1 mole, if I have 6.02 times 10 to the 23rd atoms of oxygen, I'm going to have a mass of 15.99 grams. That is what that means. We call that the molar mass. It's the mass of 1 mole. Now, a lot of this comes from an Italian scientist, Amedeo Avogadro. He developed what was called Avogadros Law, which states that equal volumes of gas under the same conditions of temperature and pressure will contain the same number of molecules. So if I have a container of oxygen, now 1 liter container of oxygen, and I have a 1 liter container of hydrogen, 2 separate containers, 1 liter of oxygen, 1 liter of hydrogen. If they have the same temperature and the same internal pressure, then they will have the same number of molecules of oxygen and hydrogen, respectively. That is what Avogadro said. So another way of talking about that is if you have 2 samples of a gas that have the same number of particles at the same temperature and pressure, they're going to occupy the same volume. It's basically restating the same thing. If they have the same number of particles and the same temperature and pressure, they're going to have the same volume. We call that molar volume. When we make it a particle, number of particles equals a mole, and the temperature and pressure we're going to set to a standard number, we get what is known as the molar volume. That molar volume is the volume of 1 mole of a gas at certain temperatures and pressures. So for Avogadro's discovery, we honored him by naming the amount of particles in a mole after him. So that 6.02 times 10 to the 23rd, 602 hexillion things is known as Avogadro's number because Avogadro was the one that helped us figure this out. Now, we did not actually get a number to it, but it's his concept of equal number of particles in equal volumes led to what we have now as the mole. And so we've called that Avogadro's number. So we now have 3 conversion factors, 3 things that equate a mole with something else. 1 mole is equal to Avogadro's number of particles. So 1 mole is equal to 602 hexillion things. Now when we say particles, we're meaning atoms and molecules. 1 mole is also equal to the molar mass on the periodic table measured in grams. So whatever mass you have on the periodic table is the molar mass. That is the mass of 1 mole. And molar volume. 1 mole is equal to the specific molar volume in liters. So let's look at these conversion factors a little bit more. 1 mole equals Avogadro's number. That's 1 mole is 6.02 times 10 to the 23rd particles. Again, particles are atoms or molecules. Atoms if we're dealing with an element, molecules if we're dealing with a compound. 1 mole is equal to the molar mass. Now this is going to be a different number for everything. So with Avogadro's number, it doesn't matter what substance we're talking about. Avogadro's number is always the same number. So whether I've got 1 mole of Pickles, or 1 mole of copper atoms. 1 mole is 6.02 times 10 to the 23rd particles, no matter what I'm dealing with. But with molar mass, 1 mole is equal to the molar mass. Well, the molar mass is different for every substance. And we find that by looking on the periodic table. So again, the mass of hydrogen is 1.008 grams per mole. That's its mass on the periodic table. That's where we find it. And we'll get into more later about how to do that. And 1 mole is also equal to your molar volume. So what is molar volume? The molar volume says 1 mole of any gas is 22.4 liters at STP. So what is STP, you ask? STP stands for standard temperature and pressure. And the standard temperature is defined as 0 degrees Celsius, and the standard pressure is 1 atmosphere. An atmosphere is a pressure unit that is equal to the atmospheric pressure on Earth at the equator at sea level. That is what is defined as the atmospheric pressure. So standard temperature and pressure is 0 degrees Celsius and 1 atmosphere. So if I have a gas at STP, 1 mole of that gas will have a volume of 22.4 liters. It doesn't matter what gas you have, whether it's oxygen, carbon dioxide, hydrogen. If it is a 1 mole of gas at STP, will have a volume of 22.4 liters. That is the molar volume. Now, it's very important that you understand that molar volume only applies to gases. We will discuss more about how to deal with that later when we do gas laws. But right now, until we talk about gas laws, we're always going to be dealing with things that are at STP. So you don't have to worry about changing the value because of STP changing, because of the temperature and pressure being different. We're just going to assume that things are at STP for right now until we actually learn about some of those gas laws. But you need to make sure you understand that the molar volume only applies to gases. Even though liquids and solids can have a volume, their volumes don't really change. Gases' volume will change based off of its temperature and its pressure. And so molar volume only applies to gases. Again, these are our 3 conversion factors. 1 mole is Avogadros number, 1 mole is the molar mass, or 1 mole is equal to the molar volume. Given these conversion factors, we can do useful unit conversions with moles. Just like we've been talking about doing unit conversions, we're going to do unit conversions with moles. And I'm actually going to get into how to do that and examples of unit conversions in moles in the next video. That's it for today. Look at the information about what a mole is. Make sure you understand that it is just a counting number. Watch that video that I have linked below of Stephen Mould's explanation. It's a really good explanation. Hopefully you enjoy it. Hopefully you enjoyed this and you understand a little bit more about what the mole is. It's an incredibly important number in chemistry. We're going to use it pretty much on a daily basis from here to the rest of the course. So thanks for watching and have a day.